the moment of inertia of the pipe I is equal to pi by 64 dO raised to power 4 minus di raised to power 4, and SB is equal to m over I into y, which is equal to m over I over y, which is equal to m over z. And we know that the z is equal to I over y, which is the section modulus of the pipe. So SB is equal to m over z. Torsional stress. This is another difficult topic. So let's try to understand the concept of torsional stress or shear stress and how to calculate it. The torsional stresses are developed when pipe is subjected to twisting moment, that is torque, which is tau over J. This is again a basic equation, you should remember it. T over J is equal to tau over R is equal to C theta over L, where tau is the torque, J is the polar moment of inertia, means Ixx plus Iyy moment of inertia along x or y axis, or it is also called the second moment of area. Tau is the torsional stress. R is equal to distance between neutral axis, means center of the pipe. Theta is the angle of deformation or twisting angle, as you can see in this picture here. L is the length of the pipe. C is the modulus of rigidity of the pipe. So the torsional shear stress tau is equal to T over J into R for tangential or twisting load. Here again tau is the torque and J is the polar moment of inertia about the perpendicular axis to the cross section, means it is resistance property of the cross sectional area. So due to twisting moment applied at one end of the pipe, it will rotate clockwise and every cross section will be subjected to torsional shear stress. Therefore, shear strain at the outer surface is equal to the distortion per unit length. Here we can consider the section B prime, which is equal to B prime divided by L is equal to B prime is equal to R into theta divided by L. L is the total length. Okay, so theta is the angle, R is the radius. So this arc length is equal to R into theta. Here theta is very small, that's why we can say that where tan theta is equal to theta. You can just consider it like that. Hence the final shear strain is equal to R theta over L. This is the shear strain. Now the shear stress, which is tau is equal to T over J into R, or tau is equal to T over J over R, which is equal to tau is equal to Ix plus Iy over R, and in case of pipe Ix is equal to Iy, so it means tau is equal to 2I over R, which is equal to 2 tau over 2Z, as we know that I over R is equal to Z, which is section modulus, and which is equal to Z over R, and Ix is equal to Iy for a pipe, mean round shape, where the section modulus Z is equal to I over R and Ix is equal to Iy for the pipe or O shape. So modulus of rigidity C, we can say that is equal to shear stress at outer surface of the pipe divided by the shear strain at the outer surface of the pipe, which is, we can say that, represent as G or C is equal to tau into L divided by R into theta. Shear stress, which is we calculated from here, when this tau divided by, which is shear stress at the outer surface, divided by this value R theta divided by L. So L comes in numerator instead of denominator. So tau into L divided by R into theta, or we can say that tau over R is equal to C theta over L, or we can say that T over J is equal to tau over R, where J is polar moment of inertia of the pipe, which is J is equal to pi by 32 outer diameter raised to power 4 minus inner diameter raised to power 4. T over J is equal to tau over R is equal to C theta over L. Again, pipe shear stress can be calculated with this formula, which is tau is equal to T into 16 dO divided by pi into dO raised to power 4 minus di raised to power 4. So the torsional stress can be calculated through these formulas that we just calculated by an example, where R is the radius of the shaft, L is the length of the shaft, tau is the torque applied at the free end, C is the modulus rigidity of the shaft material, tau is the torsional shear stress induced at cross section area, and theta is the shear strain, and theta is the angle of twist. So this angle, this is called the shear strain, and this is called the angle of twist. It is twisted from here to there. B now reach to B prime after applying the torque at this end of the shaft. Let's understand the concept of radial stress in pipe. The radial stress in a pipe can be defined as the effective stress acting in the radial direction, that is the direction perpendicular to the longitudinal axis of the pipe. The stress acts in the radial direction, which is why it is known as radial stress. The hoop stress, longitudinal stress, and radial stress act mutually perpendicular to each other. Radial stress is the stress that occurs in a pipe in the radial direction. It is caused by the internal pressure on the direction of the radius. Hence, the radial stress will be same as the internal pressure of the pipe. For thin pipe, the value of radial stress is much less compared to the hoop and longitudinal stresses acting on the pipe. Hence, therefore, it is neglected, as the radial stress is equal to the internal pressure. So the longitudinal stress in our case is half of the circumferential stress, but the radial stresses are ignored in the stress analysis due to the fact that the thickness as compared to the diameter of the pipe is very small. It means pressure is equal across the pipe wall thickness when the thickness T is less than D by 6 for thin walled pipe, and the internal pressure of the higher wall thickness greater than T, T is greater than D by 6. So we have to consider the radial stresses in that case, which is the case of thick walled pipe. We can calculate the radial stress in thick walled pipe through this formula, which is sigma R is equal to Ri square Pi minus outer radius square into Po, outer pressure, which is in our case atmospheric pressure, then Ro minus Ri square, similarly minus on the other side. So this is the formula for the thick walled pipe, but normally we don't use it. Means the radial stress is very small as compared to the axial and hoop stress in thin walled pipe, and hence neglected in this stress analysis. Circumferential stresses governs if the internal pressure is the only loading condition. So this is the case of the thick walled pipe, where Po is the outer pressure, which is atmospheric pressure, Pi is the internal pressure of the pipe, Ri is the internal radius of the pipe, Ro is the outer radius of the pipe, and through this formula you can calculate the radial stress in thick walled pipe or vessels. Sustained stresses. So what are the primary loads? These loads are generated due to the gravitational force, internal or external forces or pressures like weight of the pipe and insulation, spring force, PSV relief force, water hammer and slug, or such forces, snow or wind, etc. So due to this weight of the pipes plus internal pressure, it results in these kind of stresses. First is bending stress, shear stress, longitudinal stress, hoop stress, and radial stress. So out of these stresses, the radial stresses we ignored because it is equal to the internal pressure of the pipe. In short, sustained plus occasional loads are called the primary loads by definition. So primary loads are originated due to some kind of force acting on a pipe or piping system. So primary stresses are basically force driven stresses, means sigma is directly proportional to force. These are non-cyclic in nature. These are non-self-limiting in nature. Mode of failure is elastic to plastic. So we can say that more than 15% of lifespan loads shall be considered as sustained load, not the occasional load like snow load. So stress due to sustained or longitudinal force can be calculated as SL is equal to SA plus SB whole square plus 2st whole square, and everything is under root. So in this equation, the first one is SA. So stresses due to sustained longitudinal force, SA. This SA is equal to IAFA divided by AP plus PD over 4T, where AP is the cross-sectional area of the pipe, FA is the longitudinal force due to the sustained load, which is pressure and weight, IA is the sustained load force index. In the absence of more applicable data, we can take IA as 1. So simply we can say that axial stress is equal to FA over AP plus PD over 4T. Sustained bending moment. So sustained bending moment SB can be calculated through this formula, where II is the sustained in plane moment index, and it is taken as 0.75 or 1 in case of any applicable data is not present. IO is sustained out plane moment of index. Again, it can be considered as 0.75 or 1 if there is no applicable data is available. MI is equal to in plane moment due to sustained load, which is pressure and weight. MO is out plane moment due to sustained load. Again, it is due to pressure and weight. And Z is the sustained section modulus, means section modulus of the pipe due to sustained load. Stress due to sustained torsional moment, ST. So it can be calculated through this formula, IT MT over 2Z, where IT is the sustained torsional moment, and again its value can be taken as 1. MT is torsional moment due to sustained load, again internal pressure and the weight. Out of these formulas, when we calculate the value of sustained stress, which is SL, it must be less than the hot allowable values, which we can get it from the ASME B31.3 in Appendix A. So we must have to satisfy this condition so that the sustained stresses shall be within the code allowable stresses. Occasional stresses. Now, the occasional stresses are characterized like this, that characteristics similar to primary stresses. These are again unpredictable and act occasionally. Load act in multidirectional. Magnitude of the load changes with the passage of time. Piping system does not get time to respond to this occasional load. So loads due to wind, earthquake, snow, force of relief valve when it pop up, water hammer, and slug force extras. These are all called the occasional stresses. So more than 50% of the life load shall be considered as sustained load, not the occasional load, like snow loads. But if the snow is only in short duration, then it can be considered as occasional. Snow is taken as uniform load in analysis, so considered under sustained load. So wind shear factor, we have to input these values in stress analysis in the software, Caesar software. Wind shear factor for wall is equal to 1. When the wind it will strike the straight wall, we can consider this factor as 1. But in case of pipe, the shape of the pipe is round, so normally we take these values between 0.6 to 0.7 in case of cylindrical pipe or cylindrical shape. Then wind exposure. Again we have to input this value in Caesar software. There are 3 values given, B, C, D. For the desert, we can consider as C. Again, the structural damping coefficient, normally we take it 0.03. It is again there in the Caesar software. We have to input these values. Earthquake, normally we take these acceleration value from ASCE 7, and the acceleration due to the earthquake in term of gravity, mean F is equal to m into g. So we'll consider this force in term of gravity. For example, if we have 5 meter per second square, so we have to divide it 9.8 meter per second, and so 0.5 will be the value of g, which is the acceleration. So ux is the horizontal component of the earthquake. Normally we apply earthquake in horizontal direction, and in vertical component of this earthquake will be 2/3 of the ux. So allowable values for the occasional stresses is, as per the code ASME B31.3, is SL, mean sustained stresses plus occasional stresses. So sustained stresses plus occasional stresses must be less than 1.33 times of SH, which is hot allowable stress, as per the ASME B31.3 Appendix A. So we must have to satisfy this condition in our stress analysis so that the system will be under safe condition.